Section 7.2 Nomenclature. In a transition metal complex, the transition metal center is often bonded to several ligands of the same kind. In that case, you'll have to specify the number of these ligands. For example, if a transition metal center is bonded to 6 water molecules, and then you'll have to say this is hexa-aqua. Hexa means 6. Aqua is water. Now let's look at some other prefixes. When you have one ligand of the same kind, it's mono. But sometimes mono is omitted. All right? So if you have just one chlorido ligand, very often you just say chlorido. What if you have 2 chlorido ligands? Dichlorido. But if the ligand name is very complex, for example, if the ligand is diphenylphospheno, it's weird to say diphenylphospheno if you have 2 such ligands. So in that case, we use bis instead. Again, bis means 2. Bis is used in front of complex ligand names. Again, you can just say bis diphenylphospheno to indicate you have 2 diphenylphospheno ligands in this transition metal complex. Similarly, you use tri or tris in front of 3 ligands. Okay, so if it's just chlorido, just trichlorido, triaqua, triamine, that's easy. But again, if the ligand name is complex, you use tris. For example, if you have 3 diphenylphospheno, you say tris diphenylphospheno to indicate that there are 3 diphenylphospheno ligands bonded to the same transition metal center. 4 ligands, tetra or tetrakis. 5 ligands, penta or pentakis. Again, if the ligand name is complex, you have to use pentakis instead of penta. Hexa, hexakis, hepta, heptakis, octa, octakis, nona, nonakis, and then deca, decakis. Undeca, un means 1, so this is 1 plus 10, you get 11. When you have 11 ligands bonded to the same transition metal center, well, you'll have to say undeca. Dodeca. Now, do means 2, dodeca means 12, so it's 2 plus 10, dodeca. I usually memorize these names by the names of 4 months: September, October, November, and December. So this is just September 9 minus 2, October 10 minus 2, November 10 minus 11 minus 2, and then December 12 minus 2. I think this is just because I forgot the history of whatever country. There was a 10-month calendar. So months 7, 8, 9, and 10 were September, October, November, and December. I think that's why. Now let's look at the name of some ionic compounds. We usually name the cation first, followed by anion. A simple example is sodium chloride. Sodium first, chloride second. A more complex example, let's say potassium, aluminum, sulfate, K aluminum with 2 sulfate ions. All right, always you name the cation first, followed by the anion in the naming of ionic compounds. So now let's look at this ionic compound. The cation is a complex. The anion is just simple. It's just chloride, 3 of them. Now let's focus on this cationic transition metal complex. There are 3 plus charges, and because ammonia molecules are neutral, so this cobalt center bears this 3 plus charges. Now let's try to name this. We have 6 ammonia ligands. So 6 is hexa. So it's going to be hexa, not ammonia, hexaamine. And then followed by the transition metal center, which is cobalt. Right after cobalt, you specify the oxidation number of the metal. It's plus 3. Again, this is because this 3 plus charges are attributed to this transition metal center because the ammonia ligands are neutral. And then you specify this anions, chloride. You do not have to say trichloride because over here this oxidation number 3 tells us this transition metal complex contains 3 plus charges because the 6 ammonia molecules are neutral, the 6 ammonia ligands are neutral. Cobalt has 3 plus charges, and in total, the charges of this cationic transition metal complex is 3 plus. Therefore, you have to have 3 chloride anions to balance the charge. So that's why you do not have to say trichloride. Now let's look at this example. In this example, the transition metal complex is anionic, that bears negative charges. We know potassium is always potassium plus in a ionic compound. So when you see K2, it has plus 2 charges. Therefore, this PtCl4 bears negative 2 charges. Again, you have to balance the total charge of the ionic compound. So in this case, we again look at the number and kind of the ligands. We have 4 chlorine minus. So it's tetrachlorido. So it's not tetrachloride. It's a transition metal complex. You need to replace the ending letter E with O. So it's tetrachlorido. And over here, pay attention, it's not platinum. This is because in a negatively charged transition metal complex, you need to replace the suffix of the metal with ATE. So platinum becomes platinate. If you have chromium, it becomes chromate. If you have vanadium, it becomes vanadate. If you have titanium, it becomes titanate. If the transition metal complex is negatively charged. And also, I want to remind you, you can replace this chlorido with the common name, chloro. So if you name this tetrachloroplatinate, this is also correct. And probably is more commonly used than the UPAC name chloride. So again, if the transition metal complex bears 1 or more negative charge, the suffix ATE is either added to the name of the metal or replaces the previous the suffix um or ium of the metal. So over here um, over here ium. In here, well, a different suffix ese, but again you need to replace those with ate. Platinum becomes platinate, vanadium becomes vanadate, chromium chromate, manganese magnate. Well, this is because why the common name of KMnO4 is potassium permanganate. Sometimes Latin names are used when we try to name the transition metal complex with negative charges. So this iron becomes ferrite because the Latin name of iron is ferrum. So that's why in the periodic table you see Fe for iron. Copper, copperum or cuprum, Cu, it becomes cuprate. Silver, argentum, argentate. Gold, aurum, it becomes aurate. Tin is stannum in Latin. If you have tin in a negatively charged transition metal complex, you have to replace this with ate. It becomes stannate. Well, again, I mean, this is why the elemental symbol for tin is Sn, stannum. Lead, plumbum, Pb. So Pb, plumbum. If it appears in a negatively charged transition metal complex, the name for this metal becomes plumbate. Again, look at the ending, ate. Okay. When there's more than one kind of ligands, you may have a transition metal center bonded to several amine ligands and several aqua ligands. And then in the name of the transition metal complex, the ligands are named in the alphabetical order. So amine is in front of aqua. Okay, so in this case, this copper 3+ center is bonded to 3 ammonia molecules and 3 water molecules. So 3 is tri. You have to say triamine and triaqua. But why not triaqua, triamine? Well, this is because you just compare these two ligand names, amine and aqua, in alphabetical order. Amine is in front of aqua, so this is triamine, triaqua. The oxidation number of cobalt is 3. This is because these two ligands are both neutral. Now, in this case, we have two different kinds. We have chlorido ligands. We have amine ligands. And amine is in front of chlorido, so it's tetraamine dichlorido. When we are looking at the order of the ligands, do not look at those prefixes, di or tetra. Do not look at them. Just compare amine with chlorido. So amine is in front of chlorido, so it's tetraamine dichlorido. This transition metal complex bears positive charges, so it's just platinum. The oxidation number of this platinum center is 4. So that's why parenthesis, Roman numeral 4 here. And then why is this 4? You see this is 2+, right? But when you look at the oxidation number of the ligands, you give the body electrons to the ligands. So really you are looking at 2 chlorine minus here. Therefore, we have 2 negative charges here. Ammonia ligands are neutral, so we have -2, 0. And then the oxidation number of platinum plus -2 plus 0 is equal to +2. That means this platinum will have to bear 4+ charges. Now let's look at this case. In this case, this is just a neutral transition metal complex. The transition metal center is nickel. It's bonded to 3 carbon monoxide. The UPAC name of carbon monoxide ligand is carbonyl. So it's tricarbonyl, and then this is just pyridine nickel with a oxidation number of 0. Because this carbon monoxide is neutral, pyridine is neutral, they both use their lone pair electrons to form the bonds with the transition metal center. And then carbonyl is before pyridine in alphabetical order. So that's why it's tricarbonyl pyridine nickel with an oxidation number 0. EDTA bears 4- charges. Don't forget that, because you have actually 4 acetate in one EDTA. And in this case, this EDTA very likely forms 6 bonds with this chromium transition metal center. Overall, the charge is -1, but EDTA bears -4 charges. Therefore, chromium bears a +3 charge. The name of EDTA is ethylene, so you have CH2, diamine. So on the 2 ends of CH2, you need to put 2 nitrogen atoms there. And then tetraacetato. Tetraacetato, that means you have 4 acetate. Okay, so each nitrogen is bonded to 2 acetate. So in this case, it's going to be CH2COO minus. Okay, CH2COO minus. Each nitrogen is bonded to 2 of this CH2COO minus. And now in the end, it's not chromium, it's chromate, because this transition metal complex bears a negative charge. Okay. Now this example, this is rhodium bonded to 2 neutral carbon monoxide and 2 iodine minus. And then in this case, we'll say it's dicarbonyl, diiodidyl, rhodate. It's not rhodium anymore, it's rhodate, because this complex bears a negative charge. Okay. The oxidation number of rhodium is +1 because this 2 are iodine minus. Now, what if the ligand name is complex? This EN stands for 1,2-diaminoethane. This is the UPAC name for NH2, CH2, CH2, NH2. So you have 2 amino groups replacing 2 hydrogen atoms in ethane. So the ligand name is 1,2-diaminoethane because this ligand name is very complex. We're not going to say di-1,2-diaminoethane. We say bis 1,2-diaminoethane. The name of this transition metal complex is thus dichlorido, and then bis 1,2-diaminoethane cobalt with a oxidation number of 3. Why this 1,2-diaminoethane is neutral? This is actually chlorine minus. Again, when you see a bond between a transition metal and a chlorine, you may give the 2 bonding electrons to this chlorine to have this chlorine minus to determine the oxidation number of this chlorine, which is -1. So you have -2 from this 2 chloridos, 0 from 1,2-diaminoethane. So therefore, this cobalt has a oxidation number of 3. Okay, overall it's just 3 minus 2 it's +1, and you see the total charge of the complex is +1. So again, if the ligand name is very complicated, you'll have to use bis for 2, tris for 3, tetrakis for 4, pentakis for 5, hexakis for 6. All right. It is not common to see 7 ligands, heptakis, or more ligands. It's possible, but those are rare. All right, so one more example. You have chlorido here. You have this one is triphenylphospheno. It's triphenylphospheno, and in this case, this chlorido is placed in front of this triphenylphospheno ligand, and we'll have to use tris here to specify that we have 3 such ligands. So it's going to be chlorido, tris, triphenylphospheno. Overall, the charge is 0 because I didn't put 1 plus or 2 minus here. It's just when no charge is specified, you may assume it's neutral. When it's neutral, you'll have to look at the charges of the ligands. This triphenylphospheno is neutral. It's a neutral ligand. This ligand just use its lone pair electrons to form bonds with the transition metal. And the bond between rhodium and chlorine, it's a single bond consisting of 2 electrons. When you are trying to determine the oxidation number, give these 2 electrons to this chlorido ligand. And then you know this is chlorine minus with a -1 oxidation number. Therefore, rhodium has a +1 oxidation number. So overall, the total charge of this complex is equal to the sum of the oxidation numbers of all the metals and all the ligands. So you have +1 here, -1 here, you have 0 here. 0 times 3 is still 0. Overall, it's going to be 0. Now let's look at the constitution and geometry of transition metal complexes. So first, I want to remind you of this. When you see this formula, cobalt, Cl2, dot 6 water molecules, it does not tell us that this cobalt transition metal center is bonded to only 2 chlorido ligands. All right. So what's the real structure of this ionic compound? It's actually this. Cobalt is bonded to 2 chlorido ligands and 4 aqua ligands. And then there's 2 more water molecules in the outer sphere. So they are not directly bonded to cobalt, but they are not solvent molecules either. So in the crystalline structure of this, you have this ionic compound, but then this ionic compound is surrounded by 2 additional outer sphere water molecules. How do we name this one? Well, you have 4 water, so it's tetra aqua. And then this is dichlorido. Aqua is in front of chlorido, so it's tetra aqua, dichlorido. And then it's just cobalt, because this complex is neutral. And then you specify the oxidation number of cobalt, which is +2, because you have chlorine minus here, and you have 2 of them. Now let's look at this outer sphere versus inner sphere. Inner sphere complex means you have ligands bonded to the metal directly. So over here, 6 water molecules are bonded to this manganese. Or in this case, 5 water molecules are bonded to manganese, and then you have a sulfate bonded to manganese. So I want to tell you sometimes why I write water this way. This is a little bizarre. It's not H2O, it's OH2. Sometimes you see this because I want to emphasize this oxygen is bonded to manganese center. This is of course commonly used, but sometimes I write the aqua ligand in this way, OH2, just to have this oxygen closer to the transition metal center. Okay, so this is hexa, aqua, manganese, parenthesis, 2, parenthesis. Okay. Over here, I want to specify this. This SO4 2- is not the counter ni in the solution. So this SO4 2- is directly bonded to the metal. It's considered one of the ligands. The general name of this is sulfate. And the ligand name, you just replace the ending E with letter O. Outer sphere complex. So now I want you to look at this formula. In this case, this sulfate is directly bonded to manganese, so it's considered as one of the ligands. But over here, 6 water molecules are bonded to manganese. This sulfate is not bonded to the manganese transition metal center directly. So therefore, we say this is outer sphere complex, referring to this sulfate, not as a real ligand, but as a anionic polyoxo anion surrounding the transition metal complex. So in this case, if we were to name this transition metal complex, it's hexa, aqua, manganese, 2. So you need to put a Roman numeral 2 in a pair of parentheses, and then you say sulfate. You do not have to say monosulfate because you specified the oxidation number of manganese. It's 2+. Therefore, you can have only one sulfate. In general, let's look at the number of ligands bonded to a transition metal. The number of ligands bonded to the transition metal center is called coordination number. When you have a large transition metal ion, they favor higher coordination numbers because a large transition metal ion can be bonded to multiple ligands to form more bonds, and the formation of bonds is favored energetically. And also, if you have a large transition metal cation, it can, of course, have enough space to form more bonds. So that's why very often in the aqueous solution of a transition metal, this metal can be bonded to 6 water molecules. It's very often to see a transition metal bonded to 6 water molecules in an aqueous solution. What if the ligand is bulky? Let me give you one example. You can have 3 cyclohexane functional group bonded to a phosphorus atom to form just one ligand. It's called tricyclohexanyl phosphenol ligand. So in that case, the ligand is very bulky, and then a transition metal can only form just fewer or smaller number of bonds with such bulky ligands. So if you have, again, tricyclohexanyl phosphenol ligands, the coordination number is usually less than 4. Also, if the transition metal forms double bonds or triple bonds with the ligands, then very often we observe smaller coordination numbers. So in this case, this is, the UPAC name is tetraoxido manganate because of the negative charge here. Tetraoxido chromate because of the negative charges here. So in this case, oxygen forms a double bond with the transition metal center, and a double bond consists of 4 bonding electrons. So the repulsion between double bonds is stronger than the repulsion between single bonds. So in that case, due to the stronger repulsion between those double bonds, this transition metal centers can form only 4 bonds with 4 such ligands.